Okay, let's go to part 2 on second law of thermodynamics. This case, let's go to auto cycle, which is the gasoline engine. Great. In this case, we have the cycle. In this way, we have the initial volume, we have adiabatic compression, and then we have a ignition right here. So heat is added correct to the system. We have an expansion, adiabatic expansion, correct, and then the burnt fuel is ejected right outside together with some heat, and then new fuel is coming, correct. Again, we have compression, we have ignition, and so on. We have the cycle in this way. In this case, we have that QH right is equals to the input heat, and is equals to N more specific heat, constant volume, correct, because it's constant volume right here, times the change in temperature. Great. For QC, right, is gonna be the output heat is the same thing. Constant volume is numbers of moles, molar heat capacity times the change in temperature. But in this case, right, heat is negative. That's why we have TD minus TA. Should be TA minus TD, but because QC is negative, we just reverse write these two temperatures, correct? Now let's go to the efficiency. The efficiency, as you know, is defined as 1 minus QC over QH, correct? And then when we plug this value right here, right, NCV, right, are cancelled, and we have only TD, the temperature at point D, the temperature at point A, divided by this difference in temperature. Okay, great. Now let's see what happens when we involve the adiabat from A to B. Okay, let's do it. So what do we have? Let's use temperature. Temperature at point A, correct, times V1 to the gamma minus 1 must be equals to temperature at point B, V2 gamma minus 1. Correct? The same thing for the other adiabat from here to here. What do we have? We have that TC, correct, V2 to the gamma minus 1 is equals to TD, right, V1 to the gamma minus 1. Okay, now from here, let's solve for TA and plug it right here, and for TD and plug it right here. Okay, let's do it. So in this case, we have that TA is equals to what? TA is equals to TV times V2 over V1 to the gamma minus 1. And from here, right, TD is equals to what temperature at point D, right, is equals to TC, right, V2 over V1 to the gamma minus 1, correct? Now let's plug these values, this and this, right here. What do we have? Well, we have that the efficiency is equals to 1 minus TD, but TD is TC, right, V2 over V1 to the gamma minus 1, minus TA, but TA is TB, right, correct, 2 times V2 divided by V1 to the gamma minus 1, correct, divided by TC minus TV. What is this? Well, this is equals to 1 minus TC TV is cancelled, and we have what? V2 over V1 to the gamma minus 1. Correct? Perfect. To the gamma minus 1. Okay, now let's define this ratio in this way. Okay, let's do it this way. Let's define this ratio V1 over V2 equals to R. R, right? R. Perfect. When we apply this condition right here, what do we have? This is equals to 1 minus 1 over R to the gamma minus 1. Correct? And this is the efficiency for this cycle, right? efficiency equals to 1 minus 1 over R to the gamma minus 1. Okay, this is for the Otto cycle. Perfect. Now we have another one which is also important. We have more, but the next one, let's say, is gonna be diesel, right? Engine. For the diesel engine, we have that this is the PV diagram. The PV diagram. We have right here constant pressure. We have an adiabat, another adiabat right here, correct? And now constant volume. Right, this is adiabat. Okay, and again we start right here. We're going in this direction. This is point A, point B, right? C and D. And for this case, the efficiency is gonna be equals to 1 minus 1 over gamma times TD minus TA over, let me erase this part, over DC minus TB, right, minus TB. Okay, TC minus TB. Perfect. And this is again the efficiency for the diesel, right? Diesel, right, engine. Okay, right now let's move to the next topic. Let's go back to the ideal case, which is the Carnot cycle. Okay, let's go to the Carnot cycle and continue the analysis on this chapter. Okay, perfect. So we found, right, that for a heat engine, the efficiency is equals to 1 minus, right, QC over QH. We usually write absolute value. And also we found from the Carnot efficiency equals to 1 over TC or minus TC over TH. When we compare these two, we found, correct, that QC over TC must be equals to QH over TH. Correct? So this quantity is very important quantity. It looks like the quantity is at the beginning, this ratio at the beginning is the same as this ratio, right? At the end, it's like when we have, let's say, V1 over T1. Remember, this is for the Charles law. Remember, we did the last time, right? V2 over T2. Very similar. This is a law, right? It's a Charles law. So something like that is related in this relationship. Okay, let's work with this part. Actually, this is called the ratio heat divided by the temperature, correct, is called the entropy. It's defined as the entropy. Entropy, the symbol is S. Let's work with this picture now, and let's work with this quantity, the entropy. Okay, let's do it. Imagine, again, we work with this entropy for ideal cases. Right? Ideal cases is when we apply this to the Carnot cycle. The Carnot cycle is for reversible, right, cycles. Let's do it. Perfect. Imagine that we have a reversible cycle, correct? We go again to the PV diagram. Imagine this is the reversible cycle, PV diagram. Okay, now because we want to use the entropy, analysis of entropy, heat over time, over temperature. Okay, let's try to make small kind of cycles, right, that covers the whole, right, um, cycle, right? Imagine again we have, this is the, remember how do we define actually the Carnot cycle? One more time, it's gonna be two isotherms and two, right, adiabat, like this, correct? This is the Carnot cycle. So let's create adiabat isotherms right here, Carnot cycles. Okay, let's do it again. We have right here an isotherm, right? Adiabat, right? We have isotherm right here. Another one, isotherm, adiabat, right? Isotherm, right? Another one right here, adiabat, and isotherm, and so on. Correct? Remember the heat is added right here, so we have input heat, and right here we have output heat. Correct? Output heat. Perfect. So we have right here this no change, right? Heat input, or we can also call it QH, right? And right here we call it QC, remember? Also we call this QH and we call this QC, remember? Well, the same notation. Okay, perfect. So right here, what do we have? Also, let's say this more amount of heat, right, coming out. Correct? So when we are going back to the original statement that we found before, where it says QH over Q over TH, remember the statement, over it's absolute value, right? Q not TH is equals to what? QC, right, over TC. Well, we are rearranging, right? And what do we have? Well, we have that QH over TC minus QC over TC is equals to 0. Correct? Okay, we found that condition. Correct? Perfect. Now let's take into account this situation when we make small, right, kind of cycles, right, to create the same result for this process, cycle process. Okay, let's do it. So let's add these conditions, and then what do we have? Well, we have that this is just actually it's gonna be QH over T, it's gonna be TH right here, right? TH over TH, correct? We can use the change now, the change right here, plus, because now this becomes a negative, correct? Plus changing QC over TC. Is equals to what? Is equals to 0. What happens if we add all of them to have the whole cycle, right? So in that case, we have that sum, right, of this small changes of heat divided by the temperature amount equals to 0. Correct? Perfect. Now imagine that these changes are infinitesimal changes. What do we have? Well, now we create the integral, right? We go to here the integral for the whole cycle, right, of this change in heat over the temperature amount equals to 0. Right? That's the idea. Okay, let's see what happens then. Let's go back and create this path, right? To path. Imagine that this we start right here, right? We got to one point right here, and we return right to the same point. Correct? This is path 1, path 2, and this is point A, right? Point B. We create a cycle. The same thing, right? We are in the PV diagram. Okay, great. Now, let's apply this condition right here, right? Using we can break this cycle in two paths, right? Path 1 and path 2. Okay, let's do it. So what do we have then? We have that this integral right? For the whole circle, right, divided by of dq over t is equals to the integral from a to b, right, path 1, correct, of this quantity, correct, plus the integral from b to a through path 2, right, of the same quantity, correct, must be equals to 0. Got it? Perfect. And then what do we have? Well, we send this term to the other side, correct? And we have that this integral from a to b of this quantity must be equals to negative this integral from b to a, right, of the same quantity. But we know that from calculus, correct, that the integral from a to b is equals to negative the integral from what? From b to a, correct? From b to a. So what do we have then? So this integral from a to b, right, dq over t is equals to the integral from a to b of this one. This is path 1, right, and this is path 2. So means what? Means that this entropy, the change of entropy from here to here, doesn't depend on the path. It's the same. You can go from here to here or from here to here, correct? And the answer is the same. Doesn't depend on the path. It's the same thing as when we have the change in internal energy. The change in internal energy doesn't depend on the process, but it depends on the initial and final position. The same thing happens right here, right? The entropy change doesn't depend on the path. Depends on the initial position and final position. Correct? So in this case, this quantity is very important. The same thing as for the internal energy, right? Internal energy is a state function. The same thing happens right here, right? This quantity, which is called entropy, is also a state function. Got it? Okay, great. This is the most important part for this analysis, right? That this quantity is a state function. Perfect. This is the case, right, for a reversible processes. Perfect. And then we defined in this picture, we defined the entropy change, right? Yes, equals to the integral, right? Is defined the integral of this dq. This is for reversible processes, right? Divided by the time. Correct? Perfect. And then when we do the integral right here, what do we have? The entropy change, right, is equals to the integral from initial position, final position, right, dq over the temperature. Correct? Perfect. This is gonna be then the formula. So far, we have more, right, for entropy. Now let's involve the first law of thermodynamics. Okay, it says that the change in internal energy is equals to heat, right? What else? Minus work. Well, we can just write the differential. So what do we have? This differential of the internal energy is equals to dq minus the change in work. Correct? But look, what happens if we solve for dq? Let's solve for dq, okay? So this changing heat is equals to this changing internal energy plus this changing word, right? But the word is among the words also defined, remember, as PdV, correct? Perfect. And what should be the changing internal energy? But before that, because we got too many questions. Okay, let's go back to this one again, and then let's go back to this one. go to this one. Now look from here. Let's go and go back to this equation right here. Correct. So we have that this change, the infinitesimal change, right, is equals to what? Actually it goes like this, right? We define it like this. So it's gonna be equals to this change, right, in heat divided by the temperature. Right, from here, what do we have? Well, if we solve for this heat, remember the heat is for reversible processes. Okay, from here, this change in heat is equals to TdS. When we substitute this by over here, what do we have? The change in internal energy, infinitesimal change is equals to heat, but heat is equals to T, right, times this change in entropy, infinitesimal change, minus PdV. Okay, this is another way how we can represent the first law of thermodynamics, now using entropy. Perfect. Now let's go back again to the this equation right here, and let's solve for dq, right? Change in heat is equals to, right, changing internal energy minus P, right, dV. But what should be this internal energy? Infinitesimal change of internal energy. Remember, we define it as N, right, CV, okay, dt, and then it's equals to P, right, dV. But what should be pressure? Pressure, well, remember pressure is equals to, well, it's gonna be, right, remember from the first law for the law of the gas law, right? The gas law says PV is equals to nRT. Okay, let's use that condition right here, and we solve for P, right? P is equals to what? nRT over V. Okay, perfect. So it's gonna be nRT, correct, over V times dV. Perfect. Now what happens if we divide by the temperature? Okay, this changing heat. Okay, let's do it. And we create, right, the entropy right here. Perfect. Equals to what? And a molar heat capacity dT over T, right? Okay, this is okay, minus right here. What? nR, right, dV over V. Now let's integrate. When we integrate, okay, what do we have? Well, when we integrate these quantities, we have that this is the change, the entropy change is equals to what? It's equals to N, right, molar heat capacity times ln of T, right, final over T initial, correct, minus, right, N times R, right, times N, right, final volume over initial volume. Right, now this is another form of how we can represent entropy, correct, entropy. Perfect. So what do we have? This entropy change is equals to numbers of moles, molar heat capacity, right, and natural log of T final over T initial, correct, minus N R, correct, N of final minus initial, correct. Perfect. I can't believe it. I'm looking on the sign. Is the sign correct? Is the sign correct? Well, look, the sign is not correct. So be careful with that. Be careful with that, because remember, how do we define heat is equals to change in the energy plus work, right? So be careful with that. And then positive, positive, positive. Okay, positive. Great. Positive. Sometimes by mixing the sign, but it's positive. Great. So this is correct, but again, we send this as temperature site. perfect, we create positive. Okay, great. And this is another equation for entropy. Great. Now let's see what happens in this case. We mentioned that when the the process is reversible process, correct? The changing internal the entropy change is equals to zero, right? For reversible processes, the entropy change is equals to zero. What about if the process is now reversible, is irreversible? What happens in that case? Well, let's see. For example, imagine that we have a reservoir right here. We have another reservoir right here. This is a TH and this is a TC, remember? And we send heat from here to here. Okay, so heat is coming from here to here and we have this QH. Correct. Because in this case, heat is leaving right the system. This heat is negative, right? If we take this at entropy 1 right equals to negative, in this case QH over TH, correct? Now what happens for the entropy in the cold system? Well, it's gonna be entropy 2 equals to QC over TC. Now, what should be the entropy change, right, or the total entropy change? Well, we take this as, right, the entropy change equals to, right, this entropy plus this entropy, correct? And this is equals to, in this case, QC over TC minus Q what? Well, we can take this 2 plus 1, okay? It's gonna be minus QH over TH. Now, this is irreversible, correct? Irreversible. We're not making a cycle, it's only from here to here. It's irreversible. Okay, perfect. And then what do we have? What should be the change in entropy or entropy change? Well, let's make an example. Imagine that TH is equals to 350K and TC is equals to 270K, for example. Okay, let's find this entropy change. Let's do it. So this is equals to, because the heat is the same, right? This heat coming out from this system is the same heat going into the other system, right? So this heat actually gonna be the same at the end, correct? So heat is a constant, correct? And it's gonna be 1 over T what? Tc minus 1 over Th. Okay, it's equals to heat times, what should be Tc? 1 over 270 minus 1 over, what is Th? 350. But this difference is greater than 0. So for irreversible processes, right, the entropy change is greater than 0, always increases. Okay, perfect. So the entropy change then is equals to 0 for irreversible process, and this is for reversible processes. So in general, what do we have for this entropy change? Well, in general, we have that this entropy change is greater or equals than 0. Correct? And actually, this is another definition for the, or statement for the second law of thermodynamics, right? The entropy change is always greater or equals than 0. Is equals to 0 when the process is reversible, like the Carnot cycle, right? Or in general, right, in nature, when the process is a spontaneous process, right, the entropy change is greater than 0. Got it? Okay, perfect. Now let's see what happens when we involve uh, one more time the efficiency. Let's involve the efficiency one more time. When we involve the efficiency, correct? For example, we define that this entropy change is equals to heat over the temperature, right? Tc minus heat over Th. Tc, right? Okay, perfect. And then what do we have? Look, let's multiply everything by Tc. So what do we have? Tc times this entropy change is equals to, okay, we have right here, let's factor out heat, correct, 1 minus Tc over Th. But this is familiar to us, right? What is 1 minus Tc over Th? This is the Carnot, right, efficiency, correct? So this is equals to heat times the efficiency, Carnot efficiency, correct? Perfect. Now let's involve work. Let's involve work. How do we define work? Right, in relation to the efficiency. Remember, how do we define efficiency one more time? Efficiency, thermal efficiency is equals to work done by the heat engine, correct? That's the output work divided by the input heat. Well, the input heat is gonna be QH, right? QH, right? And what is this? This is QH2. Remember, it's just QH. Okay, perfect. And then we solve for well, we substitute the value right here, and what do we have? In this case, we have that temperature of the cold reservoir, right, times the entropy change is equals to heat, right, times the efficiency. By the efficiency is equals to work, correct, divided by QH. Actually, this is QH2. Correct? And then what do we have? Well, we have that work that were done in this process, correct, is equals to Tc times the entropy change. Correct? This is the net. When we're dealing with work, remember we're dealing with the output work, the net work. This is the net work. This is the total entropy. Also, this is called the entropy of the universe, right? Usually we use like this symbol. The entropy of the universe is the same as the total entropy, right? And this is the net work, the output work, right? Perfect. So we have then that work is equals to Tc times this entropy change of the universe. Or the total, right? We can call it total or just the universe. The universe we refers to the entropy of the change entropy of the system and the environment together, right? Together. That's gonna be the universe, or we can call it just the total. The meaning is the same, right? So again, this is the analysis for entropy. Entropy, we can define entropy also in this way. Look, entropy is defined as the measure. Entropy, right, is the measure of the amount of order or randomness randomness in a system. Okay, this is one way how we can define entropy, right? The measure of the amount of order or randomness of the system, correct? For example, we have these cases. We have this system, correct? But in this case, all the gas molecules are right here. When this is a diaphragm, when we remove this diaphragm, well, we have, correct, this expansion, right? This is free expansion of this gas. So in this case, we have low entropy, right? Low entropy. Right here we have high entropy, right? Another example is this one. If all the particles are concentrated, so they have an order, and they are right spread out, right? We increase the disorder, right? Like in this case, it's gonna be low entropy, right? High entropy, correct? And imagine that we have another case, correct? Another case, we have these particles right here, and we have these particles right here. It's low entropy. Again, let's mix these substances, and we have again all together. So this is low entropy, high entropy. Okay, to visualize in one way the entropy, the order and randomness or disorder of the systems. Okay, and with this we finish this chapter. Again, we need more information. Let's go to the book. We have more details in the book. Okay, and see you in the next chapter. Now let's start thermodynamic, electromagnetism for this class. Okay, see you in the next video. Bye.